Hi, good afternoon.
Hi Farhan, good afternoon.
How's everyone doing?
Yeah, good, good.
Okay, just give me a second. Okay, thank you again for joining on time. Uh, I do want to start right away today because we're not going to have tomorrow's session, obviously, because it's a holiday. So we want to cover everything that we intend to do today. We don't want anything to spill over. So we will just carry forward from what we did on Friday. I'm going to share the link for today's notebook. Yep. So the link is in the chat box, or you can directly go to the course repository and go to week 4, session 1, and get the notebook. You would see, if you can see it on my screen, there are two different notebooks now. There's a foosball version 2 and version 3. Version 2 is what we are supposed to cover today. Version 3 is for the next session. We still have to figure out when that next session will happen. We'll discuss that after the session. But for the time being, let's just pull out this notebook, foosball version 2, and then let's talk about the changes we are going to make today. And we have already opened the take home project that was sort of discussed on Friday, and then in Tuesday's session I showed the rubric, and we did a little bit of discussion around what the project is about. So now is a good time to like get started, explore the environment, start writing your algorithm. We obviously sort of already have figured out the algorithm. It's going to be SARSA or Q-learning. You are free to modify them. If you think you can make changes, if you think you can converge faster, get better results, if there's something you already know, because you're familiar with reinforcement learning, if you know another algorithm, you want to try that out. All of that is fine, but there are 5 different rubric items that everyone has to pass. So make sure that you adhere to those rubric points. Uh, the deadline is May 21st, which is next Friday, because then I have to like get back with the list of everyone who has submitted the project and sort of finish the course. So that is sort of a hard deadline. If for some reason you're not able to meet that deadline, then please do let me know, DM me or drop me an email and let me know your tentative deadlines, and I'll try to accommodate that. It will take some time, although we have the algorithm figured out, we know the overall approach, and it seems like a small environment, one of the easier ones that are available in the gym environment. But to really get a good understanding and to be able to solve it satisfactorily, that is going to take some time. So plan for it. You can give some time to it every day, or you can just have one long sitting and play with the different hyper parameters, different tweaks. But yeah, it's very important that we start exploring the environment right now, because there are things to be found there, like small differences from the environment that we implemented foosball versus gym. So that will only become visible when we start exploring and writing algorithm, and then plotting our graphs and seeing what is working and what's not working. Okay. So I'll then switch over to what we have to do today. Like we discussed last week, Week 4 is about introducing more realism in the environment. So far, everything has been static. It has been a really tiny, tiny environment with just one moving piece. And we know that this environment could have been solved using a variety of algorithms, right? If we had complete information, it could be solved just using dynamic programming or one of the shortest path finding algorithms. If we didn't have that at our disposal, if we didn't know the underlying single step dynamics, we could still already implemented an algorithm that was able to converge pretty fast. In a few thousand steps, you sort of figured out the shortest path from every location on the field to the goal post, avoiding all the defenders, your opponents, right? Uh, but this is not why we are here. We want to solve more complex problems like the one we had in the beginning, where you were trying to control a car, or it could be something like controlling the movement of a robotic arm, or it could be something like allocate some sort of resource allocation where you are interested in minimizing, uh, maximizing some sort of long-term reward, right? So we want to solve more realistic real-world problems, and to do that, we are again going to tweak our own environment a little bit. uh, what we are going to do today is we will introduce uncertainty. That is the first thing that sort of comes up, gets in your way when you are trying to solve a real world problem. So far, we had an environment. Whatever action you selected, the environment responded by executing that action as long as that action was possible. But the action was executed even if the outcome was that you still stayed in the same state. The action was nevertheless executed. Uh, in a more realistic scenario, actions will be always be uncertain, in the sense that if there are many different, oh, I'm sorry, so that isn't the full URL. The full link is now in the chat box. But even if you have the incomplete link, I think if you open GitHub repository, you would see there are two different notebooks, and we are using version 2 today. Right, so make sure this is open. Uh, I have the instructions. The environment is largely the same, but we are going to make some changes. Those changes are highlighted over here. So if you look at the description, the thing we are going to change today is that we are going to associate some uncertainty, some stochasticity, some probability with the actions, the way actions are executed actually. So what we want is that anytime I want to execute an action, let's say A, so with a high degree of certainty, with a high probability, that action is executed. But there is a slim chance, there is a low probability that one of the other action gets executed, right? And for this environment, this makes all the more sense. We are playing a game which is like football or foosball. So there is always a small probability that if you want to take the ball in a particular direction, the ball slips or the player slips or something happens, and the ball ends up in one of the other states, right? So if you see, if you look at this line, then this is what this is saying. The other players are still going to be static. That is something that we want to change in the next session, in the next notebook, where we are going to allow other players to move around as well. So we don't want to take a big leap. We will go step by step. Right now, we are going to make the actions that our player, the agent, is going to take. So we are going to make those actions stochastic, right? And we'll come to that in a little bit. But this is the fundamental change. Like we're going to come to the exact changes in a little bit, right? In terms of rules, so basically, when you select a direction to move the ball is going to sometimes slip away and get into one of the other cells. And again, to keep things simple, we will just assume that there's a slim chance that it will end up in in any of the other cells. So if I want to go up and I select action north, the ball is likely to go north, but it might, with some small probability, also go east, west, or even south. Again, this is rather arbitrary, and we can tweak the rules. We can, maybe we just want, we think that going south is not feasible, so we might have different probabilities for different uh, you know different outcomes. But right now, again, to think keep things very very simple, we will just assume that that small probability is sort of spread over all the possible states, right? uh, so sort of bad action is equal, all the bad actions are equally likely, right? How are we going to do this in terms of code? So first of all, we are going to introduce a small parameter so that this is programmable. We can have as much probability, as much stochasticity as we like. So we are going to pass the foosball class a parameter that we are going to call sleep probability, right? This is the probability that something unintended happens, right? And in our case, because there are four actions, so this is the total probability that one of the three other actions happen, except for the action that we intended. And because of that, one minus sleep probability is the probability that the selected action gets executed. Uh, what are the changes that we need to make to the environment, to the class? So of course, init is now going to take another probability and the parameter sleep probability. And what we want to do now is, and this will become more familiar once we start looking at the code for the taxi environment. Uh, and so the way we are going to implement this is that, okay, now for every state and every action, earlier we used to have a pandas data frame. We didn't really have a data frame within the class or within the environment. But if you wanted to store the outcome of every action in every state, you would have some sort of a 2D array or a table to store that, right? Now in this case, when there's probability involved, we are going to require a 3D array, because for every state and every action, there is a distribution of outcomes. There are many different states that are possible, right? And typically you would just want the third dimension to be all possible states, even though there are some restrictions. So what I mean by that is that uh, you have the first sort of dimension is your current state, the second dimension is the actions, which has size 4, the third dimension is again going to be all the states, which will have size 20, right? So in any state you take an action, there are 20 different possibilities, even though we know that realistically only there are only at most 4 possibilities, because the way we are implementing the rule is that you can only, the ball can only slip away to one of the 4 neighboring states. So not all the 20 states will have probabilities. Many, most of them, 16 of them will have probability 0, 3 of them will have some small probability, and one state will have a larger probability. This is the idea, and we can store it in a 3D table, probably a numpy array. And so in terms of code, what is going to happen now is that init will call this method which we are about to implement, and then this method generates a table or numpy array which is three dimensional, which has shape 20 into 4 into 20, and then it's going to populate that, right? And really what we want to focus is on how to populate it, how to get the probabilities correctly distributed. That is going to happen inside this new function that we will create. We'll call it set state transitions. uh, and there is another change which would be required, because now the outcomes are not uh, they are, they are going to be probabilistic. So the function that we used to call get next state on action, which used to return a single state when the environment was deterministic, we are going to change that function. We are going to rename it to get likely next state on action, right? So now that the next state is not 100%, we're not 100% sure that that is going to be the next state, but nevertheless that is still the most likely state. So we just rename the function. The guts of the function, the logic of the function sort of still remain the same, because it just has to pick the, it just has to assume that the correct action was executed and then return the next state based on that. We do introduce a new function, a new method, which is now going to be called get next state on action, which will take state action like this other function. But now this returns you a probability distribution. So it returns you all the states and their associated probabilities, right? or probably still better, because we don't really want to return a distribution to the agent. The agent is outside the environment, it's not aware that the environment may be stochastic. So we don't really want to tell it that it is stochastic and return it an array of all the possible states. We will return it one of the states. So we will internally within the environment we will pick an action, uh, which may either be the correct action or one of the bad actions, the unlike the undesired actions, and execute that action, and then whatever is the outcome of that action, we will return that. This is the idea. So let's start. Let's execute the first cell. Again, this template is again going to look exactly the same that we had earlier. There are no changes over here. Right, the notebook, if you have joined later, so the link to the notebook is in the chat box. Right. This is the class. The other functions are still the same, so I'll just move over them. Init has a few changes. The first change, of course, is we like to introduce a parameter here that we're going to call sleep probability. So you that is just a change that the to do already indicates that change has to be made here. And then over here init is calling this function with and passing it the sleep probability. The rest of init looks and feels the same, but if you come down, then this is the function that we used to call get next state on action. Now this is get likely next state. uh, the logic is exactly the same. There are no changes at all, right? Because this is just assuming that the environment is behaving deterministically. So it takes an action, it takes the current state, it tells you what the next state is going to be, right? If there was no slipping involved. So the first thing we need to implement is the new variant, right? This thing called get next state on action, which is our new version. Now this is of course going to factor in the stochastic nature. So and to do that, it is going to depend on the three-dimensional table that we talked about, right? So it will just look up that table, look up the state, the action, and it will get a distribution, and then it will we will see, but it will return one of those states, right? Idea is really simple. So you can look up the state and action, and then you have 20 different likely outcomes, and you have probabilities. So you pick one of them using the numpy.random.choice API that we have used earlier as well. But really, to implement this method, we will have to implement this method first, right? This is where the table is getting constructed, right? So this is going to be a three-dimensional table, like I said, number of states by number of actions by number of next states, which is like 20, 4, 20. So the table code is already here. All we need to do is fill up this table according to the rules. And what are those rules? I already said that we will take you have to fill up every state and action pair in this table. So for every state and action pair, now there are going to be 20 different possibilities. And to fill up those 20 different possibilities, you have to consider the fact that when you are in a state and you take an action, so with one minus probability of slipping, that action is executed. With the other with probability slip, the rest of the three actions get executed, right? So there are 20 likely outcome states, but really only four of them are going to be populated with the probability. So all you need to do is fill up this table with the correct probabilities. These are the changes that we need to make over here, and then uh, then we'll proceed from here. We'll create an object. We will do some sanity testing over here just to make sure that probabilities add up, and then we will see if we need to if and where we need to make changes to the rest of the code. So we have sampling code, we have episode generation, we have the actual algorithm, SATSA, Q learning. We'll think about which places will require change because the environment has changed now. Okay. Uh, so I hope this requirement is clear to everyone that we need to implement the lookup table first. That will just tell us what are the probabilities for the next states, and then we need to, based on that table, we need to implement this really small function. This shouldn't be a lot of work once we have the table. So again, now this is going to require some thinking and a little bit of experimentation. So I will open the breakout rooms, and we can give it, I think, at least 15-20 minutes try to implement this. I will hop from breakout room to breakout room, but let us give it a try to build that table of probabilities. Okay, so did anyone try to implement this? Am I audible? Can you hear me? Okay, cool. So essentially, what we wanted to implement was just a bunch of for loops so that we can fill up this table, right? This is a three-dimensional table, so you have to loop over all the three dimensions, uh, sort of. But we can actually take a shortcut. We may not have to. We can sort of cut down on the for loops, and I'll show you in a bit what I mean by that. So of course, it is one thing we do know is that we need to the first top level loop is sort of going to go over all the states, right? So it will look something like this. So you're just looping over all the states. Then you must have another loop that goes over all the actions because that is what we want to fill up this table with, right? So you need to you need at least these two loops. Um, Now I can have a similar third loop, which is again listed inside the second for loop, which will go over all the likely states. But what is far easier for me is just to have this third loop over the possible actions, right? And I'll show you what I mean by that, right? So I can have the third loop which looks a bit like this. So this is, I'm calling it bad actions. I'll explain why I'm saying so. But this third loop is just again looping over actions, not states, right? So although the third dimension of the table is 20, which is the number of states, I have this loop for only bad actions, which makes sense because the table is already filled with zeros. And we discussed that whenever you are trying to execute one action, which is sort of this action, there are four other possibilities. There are a total number of four possibilities for the actions that will occur. So instead of considering all the 20 possibilities of the all the outcomes, I can just consider the four actually possible possibilities because that is how that is the restrictions we have put that the ball will only go to one of the neighboring states, right? So this is a little bit of an optimization. Uh, Over here I have to loop over action indices now. Earlier we were directly using actions, which was those strings north, east, south, or west. Now we can't do that anymore because we have a numpy array, so we must index it with numbers. So that is why this for loop is using indices, numeric indices, and the other one too, right? So we have two for loops for actions. The top for loop is going over the, you can say, the executed action or the intended action that, sorry, the intended action that came from outside the environment, right? So this is what the agent sort of told the environment to execute. The inner for loop, which we are calling bad action, is the action that actually happened, right? This is what the environment ended up simulating for you because there's a possibility of actions going wrong, right? So what we want to do is we want to test if the intended action was the, and probably calling it something like, just calling this one intended action or this calling this executed action will make more sense and be a little less confusing. But the first thing we want to do is compare if these two actions were the same. So for this case where the intended action and the next action are same, it's really easy to figure out everything. Like we can figure out what the next state will be, and we already saw that we repurposed one of the APIs. We renamed one of the previously created APIs. So this API that we are calling get likely next state, this is going to tell us with certainty that if this is the action and this is the state, then what will be the next state, right? So we are just utilizing this API and I pass it the state. And over here, because this function was still intended to work with actions that were strings instead of numbers, So I have to do a little bit of translation between the two, but the idea is very simple, right? And this, what this gives me is the next state, and then I can use this next state to populate my table, which is going to look like this, right? Uh, so this has to be understood very carefully. So this is the table. We are in a state. This state, we have just executed this action index. Again, in this case, action index and bad action index are same, so you can use any of them. And the next state we got from here. So for this combination of state, action index, and next state, because this condition is being met, because this is the actual action that we intended, so we will assign it the larger chunk of probability, which is 1 minus probability select. Right now, there will be a complementary case where this is not true, right? So the next state, so the next state comes from executing some other action, right? So that action is not the intended action. But whatever action it is, we can still rely on this API to give us the next state, because it always tells us the right next state if that was the action that was executed, right? So the first line is not going to look very different. Again, over here you could have either used bad action index or action index, because they were equal. But over here you have to be careful. So this is how you get the next state. The next line is also going to look different, right? This is, so state and action index, they are going to, the important thing to understand here is that we are filling up the table for the action that was intended, right? That the agent desired, not the action that actually happened. In this case, the two are different. So over here you still have to use action index. Now we can't use bad action index over here. Um this is something that we have to be aware of, but the other indices make sense. So next state is next state, and state is state. Probability, of course, because we passed it a small number like zero point 0.1 or something, and that was the probability of being in any one of the bad states. Like that was the probability of executing any one of the unintended actions, right? So I can just safely take the number of actions, subtract one, which gives me the number of unintended actions, and then I'll distribute that probability over this next state, right? Additionally, because we may want to debug things, so I'll just insert two lines of code over here, which is right now commented out, but this is just tracing the operations that we are doing. So in both the cases, I'll add one extra line of code that gives me everything that I need, right? So this basically, we will enable this if we ever want to make sure, if we want to debug to understand how the table is being filled up. But this is the logic. Now let me know if there is any confusion about this logic, or if there's a different approach that you thought of or implemented.
So why are you doing a plus equal to here? I'm not clear.
Yeah, this is interesting. So plus equal to is required because you could end up you could end up in the next in the same next state by executing different actions, and this is basically going to happen when you are in one of the cells which is next to the boundary line. So think of the state, when the current state is 0, and you take action index 0, which corresponds to going north, then you end up back in state 0, right? So state 0 and action 0, and that brings you back to north, right? Um, but there could be other actions that take you to the same next state, right? For example, when you are in state 0 and you take action 1 which corresponds to going east, there's a tiny probability, because actions are uncertain, there is a tiny probability that although you intended action 1, the real action was 0, and you again ended up in state 0. So in both these cases, the probability of being in this state, uh, so the probabilities have to sum up in this case, because uh, again you are going to be in the same next state. And you can
But your
actually,
action index is different, right?
right, sorry, okay, so let's think of this in this way. So let's actually run this. Right, I'll show you in a moment. Let's keep the code as it is right now. I just enabled the logs over here, and very quickly go back to this function, which is the get next state on action. And this is nothing but this just has to pick one of the states from the all the possible next states, right? So this is going to be really simple. We already know that numpy.random.choice can help us do that. So I'll just copy over the code and explain it. Right, so the assertion is just a safety check, it remains there. The only thing that changes is that this API is still accepting actions, so we need to convert from action to action index, which happens over here. And then of course we already have, we have supposedly built up this table, the p table. So all we need to do is pick the state, uh, pick the action which is the real action which that was intended, and substitute this over here. Now this is going to give me one slice of the table or the numpy array, right? So this is going to be give me an array which has 20 different states, and all I do is sample from those states, right? So these are the probabilities for those 20 states, and these are the actual states, and I just sample one of those states and I return that state. Now we know that although this is an array of size 20, only 4 of these probabilities will be non-zero, so that is not an issue. So whatever this next state is, it is always going to be a feasible state, right? With this implementation, right, I'll just try to run this code. Yeah, I still have to fix my init function. Oh yes, so I forgot inserting this check over here, but you want to do this, but you definitely don't want to touch the terminal states, right? So although this table is going to have all possible states, we know that the game doesn't really allow taking any sort of actions in a terminal states. So we better insert a condition over here that just exclude that possibility. So right inside the for loop for states, we first check if that state is a non-terminal state. Right, this check has to be there. So we only perform, because for terminal state it is going to be all zeros. Okay, so now I enable the traces, and let's go back and look at what is happening. right? So state 0, for example, action 0, and bad action 0. So this is when the actual action gets executed. So obviously, because we are passing a probability of sleep probability of zero point 0.1, so the probability that is being assigned by our code is zero point 0.9, right? Because this is the intended action. The action is 0, and the action that gets executed is also 0. So obviously, the probability is zero point 0.9, right? Just look for the case where this is getting its additional probability, right? Uh, so uh, for example, this line over here, right? So this, you were in state 0, you intended to execute state 0, but what actually happened was you actually intended to execute action 0, but the action that actually happened is action 2, which would be north, east, and west. So actually you tried going west, and we know that if you are in state 0, you are in the top left corner, you can't really go west. So that will again bring you back to state 0, right? So the example I was trying to show, that was not right, but this is definitely possible. So if you go back here and think about what is going to happen, 0 0 0. So you're in state 0, you take action 0, and the next state is 0. This should get a probability of zero point 0.9, because this is the desired action being executed. But what happens if you take state 0, your intended action is action 2, and your executed action is action 0, right? We are not factoring the executed action over here in the table. But if the executed action is 0, then obviously you are going to come back to state 0. You tried going west, and you ended up in the cell. Now at this point, this probability is going to be the probability of, the action misfiring or bad action happening. So this is going to be zero point 0.3 or whatever it is, 0.03, right? And that is why you want to sum up the probabilities, right? Because this is, again, this is going to be 0, this is not going to be 2, because this is the action that you tried, right? So you still tried going north, but the action that really happened was going west, and because of that, these two probabilities should sum up. And this should also make intuitively make sense if you just look at the north state in isolation. Then there are ideally there should be four different possibilities. So one possibility should have probability zero point 0.9 associated with it, and the other three possibilities should have a zero point 0.03 associated with them. But then two of those probabilities bring you back to the same state, right? And that means that the probability for that transition to happen should really be higher than just zero point 0.9, and that is why you need to add up the probabilities. Is this making sense?
Yeah, thanks.
Cool. Right. So with this in place, we are sort of set up to execute this new environment where you have some slipping, some uncertainty. So the first thing we would like to do is, sorry, I keep selecting that. First thing we would like to do is just go ahead and run the next cell, which you should probably disable. You already have this disabled, but if you enabled it, then just turn off the logging and just run the next two cells. And there is, right, there is this sanity check over here, which basically tests that your probabilities are summing up to 1, right? So for every state and action pair, there are 20 different possibilities. So does the probability of those 20 different possibilities sum up to 1? This is ensuring that before I run the next cell, I would just like to actually look at one of these, state action pairs. So for example, p of state 0 and intended action 0. What does it look like? Sorry, foosball p, right? right? So just need to quickly check that this is actually making sense to us or not, right? So this is for state 0 when you take when the agent tries to execute action 0, right? And we know that for example there are different possibilities when you try to go north. You could actually go north, you could actually go west, uh, or you could go east, or you could go south, right? And look at the states over here. So this one of course is coming back to the same state Z. So this is of course an array of size 20, right? So all the possible next states, and the only states which have non-zero probabilities are state 0, state 1, and I think this is state 4, which is for going south. So this one makes sense. The probability of going south is 0.03. This one also makes sense. You are trying to go north, there's a small chance that you end up going east. This is the one that we were discussing, which is when you try to go north, there are two outcomes. You actually go north, and that brings you back to state 0 with a probability of zero point 0.9. You could also slip and try going west actually, which will again bring you back to the same state with a probability of 0.03. So that is why things add up over here. We can also look at state 1 and 0, right? So you're at state 1, you try going north, right? So there are four possibilities again. You will either actually go north, so the probability will be zero point 0.9, and you will still remain in the same state because 1 is also next to the boundary line. So this is the probability over here. You could slip and go west, probability is over here, or you can go east, or you can go south. In this case there are no such cases where probabilities add up, so this is zero point 0.3 over three different states. If I try to go east from here, there is a defender in the next cell, right? So again, but that doesn't really block me from going east. So these are the probabilities again. They're differently distributed. So this is really going to affect the cells which are in the corner where you have the same desired action bringing you back to the same state in different ways. So this you can look at different states and make sure this is making sense to everyone, but this is the idea, and this is the sort of the length 20 arrays that we were looking at. These are the arrays from where our function is going to pick one of the states, right? This is all this function is doing, and we saw that most of the probabilities, 16 probabilities, will be zero there, right? So let's just go ahead and render this one. Looks okay. uh, then it's important to actually interact with the environment now and see if that this is actually happening. Like if there is some probability. So right now the ball is over here. Let's see, we want to take it east. It does go east. Let's try south. Goes south because zero point 0.1 is a small probability. And yep. So you won't see the probability in action every time. Two of the actions executed in the desired way. I went east, I was able to go south. Uh, then when I was here, I tried going east, right? But that didn't really happen. So we actually ended up with that small probability. We ended up colliding with going south and colliding with the defender there, right? So this does seem to be working. So occasionally you will have those instances where your intended action is not getting executed, right? The rest of the code here is same. So I'll just execute it. Get discounted return. This doesn't really get affected by anything because uh, this whole simulation of the probabilistic nature that is going to happen within the environment. So we will feed it an action. It will give us a state. That state will sometimes not be the state that would have been if the correct action was executed, but that is fine. We are just generating an episode. So whatever state we get, then we again feed it some action. So get discount return is not concerned with all of that. It just executes the environment. It keeps running the environment, and then it follows a path. The thing that is going to change is that if you take a path and we ran this function with many different paths. So if you take one of those paths and run this function again and again, get discounted return is not going to return you the same value every time. Occasionally it will stray away from the right path because it internally the environment executed another unintended action, right? So you will see that in action here. This is not going to remain unaffected, but there is no change in the logic, right? uh, what about policies? So we had this function that selected the greedy policy. Again, this is not going to be affected in the sense that we don't need to change the logic in any way. uh, the idea is still the same. Your policy is the action that gets you the best return in every state, right? We hopefully will be able to build a return table even in the presence of all the uncertainty, and that table is again going to guide us. Even if there is uncertainty, that table is always going to tell us what is the best action to take at any moment. So even though the environment has stochasticity, our policy is not going to have any kind of stochasticity. The policy is still going to give you the best action to take. Following that policy, you may not be able to get the best result all the time, because obviously there is stochasticity within the environment. But now the idea is that the policy should, the expected return that the policy gets you should be the best expected result, right? That is what we expect from the optimal policy. So it won't maybe it won't take you to the goal state every time, but it should take you to the goal state most of the time, and it should get you the best return for the, so follow the shortest route and everything, right? So right now the policies we are dealing with, they are not going to be stochastic in any way, right? This is just a helper function. This is not going to change. uh, what about episode generation? Is there something that we need to change here because the environment is stochastic now? Because now then we are going to use this episode generation for interacting with the environment and learning about rewards and everything. Is there anything that has to be changed for episode generation? Okay, if you think very closely about how we have been dealing with this, so the whole idea has been that over here you have an environment that we are going to treat more or less like a black box. So you interact with the environment and you get to know about the environment. So even if there is a new addition, if there is stochasticity present, we don't want to make any changes, and our hope is that we are still able to figure out the presence of that stochasticity. We won't explicitly measure or try to ascertain how much stochasticity is there, but hopefully when you are interacting with an environment, you will get an idea, some clue about the environment not behaving exactly the same way every time, and then your algorithm is sort of able to deal with that, right? But as far as episode generation is concerned, there is no change to be made. You still start with the initial state, you still feed it random actions, because this one over here is for random action generation. Now obviously internally there will be differences. So uh, now there are two factors at play. One is the random action selection, because we saw that when you ran this code you got a different episode every time. But there is also this internal stochasticity. So this will just add to the uncertainty in your outcome, right? You can run it many times, you still get many different episodes, because now there's even more probability involved. But you don't have to make any changes to the logic of the code, right? The discounted return from episode isn't going to look any different. This is again going to be entirely what we were using earlier. uh, okay, this function again, it's a stochastic environment, no doubt, but this function is about creating an epsilon greedy episode using a table, right? and it doesn't really have to bother about what is going on inside the environment, right? So it doesn't get affected. You can read this function line by line. So these are the actions, they remain the same. The action probabilities are built by us. These are because we have an epsilon greedy policy. So we built up this array. This has nothing to do with the probabilities inside the environment. And then the greedy action happens. The greedy action comes from the table. This has nothing to do with the environment. And because of all this, there is no change required over here, right? So the only change that we really made was within the environment. We made the environment different. We made it stochastic. But outside the environment, so far there have been no changes. This might change when we allow for players to move around, but right now there are no changes. So then the question is, can our algorithms learn this behavior? Can they sort learn in the sense that the policy that you get, is it still able to perform optimally most of the time? So the code is already there. This is the code that we wrote 2 3 sessions back. This one generates entire episodes, and then from that experience builds up a table. So we just run this code again for 5,000 steps, and then we'll try to print the policy and see uh, how well the code performs. With, if you remember last time we did this with 5,000 steps, we were able to get very close to an optimal policy most of the times. So with all the hyperparameters and everything remaining the same, the only real change is that the environment now is a little unpredictable. Right. So the policy is getting printed. Again, looks like we are caught in a loop over here, but largely the policy looks okay. It looks like if we tweak the parameters, if we train for more number of episodes, if we tweak other parameters, then probably you will get a policy, because this seems to be inching towards the correct or optimal policy, right? So despite there being uncertainty in the environment, if you train it for enough number of episodes, then the table will get updated. The table, of course, will look different. The numbers here will probably look very certainly look different, uh, but the the actions that correspond to the best or the highest return, that will still be correct at the end of the day, right? And that is what matters for us. So this seems to be working. uh, Again, we can run the other pieces of the code. We implemented sarsa and q learning. So let's try to see if sarsa or q learning or both of them are able to get us results. Right, and these are, again, the code is exactly the same that we were using in the last session. And as early as 500 episodes, you see that the policy is almost optimal, right? So between 500 and 1000 somewhere, it's able to hit that exact optimal policy, right? So it doesn't seem that there is a great deal of uh, sort of challenge that that the policy or the algorithm is facing from the changes in the environment, right? And we can do the same for q learning. Again, there is no reason that it won't work, right? So we can run the q learning code, and we will do that. There is, this code is still incomplete because there are a few changes. So if I were to run q learning, then of course this will give me a policy which looks something like this. This is going to train, this is going to work. What I want to do is, there is some addition. There are a few things that we want to track now. And uh, what uh, what I want to do is, I want to be able to track the rewards that I'm getting along the way. That is going to help us deal with debugging scenarios for this scenario and when we are attempting the project. So it's important that we keep track of the reward. That tells us, number one, if the algorithm is learning or not. So whether the number of the parameters you are using are they helping the algorithm learn, and when does the algorithm hit a point where there's saturation and then it stops learning, and then it's totally unnecessary to train beyond that point, right? And the idea is that if you were to look at rewards for individual games, individual episodes, that is going to have a lot of spikes. So it will include a lot of noise, and it will just look zigzag and all over the place. What makes more sense is to take an average, right? So if I'm training for 2000 episodes, perhaps I can take the average of each of the 100 episodes, each sequence of 100 episodes, right? So sort of have a sliding window. There are 2000 different episodes. You will have 2000 different rewards at the end of the episode. We want to take the average of the first 100, then we want to take the average of episode of, first 100, I mean episode 1 to episode 100, then take the average of episode 2 to 101, and so on, and then plot that. Uh, that should be more smoothed out. You should see less variance, less noise, and that should give you an idea of where your uh, learning or where your training process is headed. Is it going for saturation? Is it learning at all? Questions like that. So we can answer with that. So now the idea is, basically that let's have a numpy array or a list over here, and then let us have a variable over here that we can call episode reward. Okay, so just before you start episode, you initialize this variable to 0, and you just accumulate the reward that you are getting within that episode. And at the end of the episode, we just need to store this. So there should be an array which has, in this case, 2000 entries, and we will store it at the appropriate place, right? And then after this training process over, I would like to compute the averages, and I would like to plot the average reward and see what is going on, right? So let's take a few minutes. Like there is nothing novel going on over here. The only thing is we have to think about is what sort of rewards we want to track, right? So because we are trying to gauge the performance of the agent, we are not accumulating rewards to train the agent. We are trying to assess its performance. So think about that and fill in the code, and then we'll see how to compute the averages. Okay, so this isn't really a challenge or anything. What we can do is just create an array, fill it with zeros, and then I'm calling it rewards, and then this variable is accumulating the reward for one episode. Then at the end of an episode, I just write it to the array that I generated, right? This should work. Okay, with 2000 steps again, we got a policy that is optimal, but we could have gotten an optimal possibility with fewer steps as well. And that is what we want to figure out, if 2000 steps was adequate, if we should have trained for more steps, because this policy would look different at every step, right? So have we attained have we attained that point where the policy has sort of become stabilized, and even if you were to train it for more steps, it's not going to change, or is it still changing and the values are moving up and down, right? uh, so what we have these rewards array, right? This has all the 2000 rewards. We want to take a shifting mean. There are different ways. We can just write a for loop and loop over all the positions, and something like rewards of I to I plus 100, and then I has to be adjusted so that you don't go outside the bounds of the array. But obviously you can take averages like that. That is not the challenge here. But the way I typically implement it is with something called np.convol, which looks like this, right? I discussed this in the last session, but this is really simple. Take the rewards array, and then whatever your window size is, construct another array, right? This array has ones, and this has length 100, and it has it's filled up with ones. Then I divide it by 100 so that each of the entries is zero point zero 0.01, and then I'm passing these to np.convol, and np.convol is really simple. It will just take your this rewards array, it will take this sort of window array, and it will slide the window over the rewards array, and it will compute the you can say the dot product at every point, right? So if you're familiar with convolution, this is what convolution does, right? So there is a sort of signal or whatever you call it, and then there is this weights array. So this is your weights array. This is zero point zero 0.01 because when you're trying to find the average of 100 entries, so you will obviously divide by 100, or you can say multiply every entry by zero point zero 0.01, right? And then I can just go ahead and plot this window reward. Right. So no matter how you compute this average reward, this is of course this won't have a length of 2000 because the last the, when you stop taking the average when you're around 1900 or so. So, but if you look at the averages, even this averaged out version has a lot of spikes, right? And these spikes will be there because it's not a linear process when you're using one of these algorithms. So there will be instances where the table sort of becomes very good, but then it sort of depletes because you are still trying random actions. We have an approach where we're mixing random actions and the table based approach. That is going to happen. But what is interesting is sort of that if you look at the overall trend, then the peaks are going even higher and higher, right? So over here we had one peak which sort of gave us what was still a negative reward, but then you reached another peak, then another, then another, then another. So this is the averaged out reward, right? Remember that. uh, and looking at this graph, there is no hint that we can't get an even higher peak if we were to train for more episodes, right? So we can probably try 5000 episodes and see how this graph is looking like. But if this graph had saturated out, which I can probably show here. So I don't know if I have a graph, but yeah, it could have saturated out and look like something like this. So in this case, the algorithm was supposed to train for 20,000 steps, but over around 2,500, or you can say even 5,000 steps, this becomes very flattened out, right? So there's no chance that the algorithm is learning after this point. And so if we are experimenting, we can be sure that with these parameters, 5,000 steps is the most you want to go. So in this case, that is still not the case. So we can uh, still keep going. We can probably get better results because you don't know. This is one instance. If I run it again, you may or may not get the same optimal policy back again. And what we really want is we want to reach that plateau where where you're consistently getting the optimal policy. So you don't have to worry about some of the actions being flipped around because your policy was unstable at that point. Right? This doesn't look good because now there are big issues over here. These arrows are not pointing in the right direction. So there is some more training required, and that was being reflected over here. Right? If it had flattened out, then you can be sure that okay, over the last 1,000 episodes or so, we have been consistently getting the best policy. And you also have to think about the rewards that you are getting. Right? The better you get, the better policies you have, the better rewards you get. And considering the reward structure that we have in place, where you don't get any reward at all for taking the steps, and you get a reward of +5. So ideally we should train it to a point where these peaks, where when the saturation comes, you are able to hit the reward of 5 or somewhere around that, because this is an average version over 100 episodes, so it may not be exactly 5, but you should be close to 5, and we are still far from there. Right? So this is very important. This is going to give you that bit of information. The other thing I want to sort of talk about is how we are, what the exact value that we are accumulating over here. So we are not discounting the reward anymore when we are keeping track of it. And that makes sense because eventually the thing we care about is the sort of reward that your agent is able to get when it gets deployed, when it is able to, when it is trying to work or function in that environment, right? The whole point of decaying the reward or using gamma was for the sake of training. So we didn't want the training algorithm to pay too much attention to rewards that you were getting far out in the future. And there could also be tasks where there is no clearly defined end of the task, so they may not be episodic. Because of all those things, we introduced gamma very early on. We talked about the reward structure and returns and discounted returns. But when you're trying to assess the performance, you shouldn't discount the your returns. You should just accumulate the rewards as you get, and then the sum is just your return, right? So this is where we are now. One more thing that we want to try out today is another variant of SARSA that we haven't talked about. So we saw SARSA, we saw Q learning. The difference was that Q learning just picked the best action. SARSA picked a silent greedy action. But there is a third possibility where you can implement what is known as expected SARSA, right? And it will probably give us better results if the environment is stochastic. The idea is very simple, that over here in this step, uh, instead of selecting max, instead of selecting one action, why can't we just take the expected value, right? And what do I mean by the expected value? So let's actually look at the code for SARSA, right? So we are selecting one action over here, which we are calling A1, and we select the Q value for that action. But what if we consider all the other possibilities, the other three actions as well, and then we weigh them by their probability, the probability that comes from the policy that we have defined, right? So right now the policy says it's an epsilon greedy policy, and depending on the exact value of epsilon, it would say that A1, the best action has a certain probability, and the rest of the actions have some other probability. So why can't we just instead of picking a single action over here, let us do that in a more uh, you know Q learning sort of way. So we don't select a single action over here. Let's consider, but we still consider the value of the Q value, the Q value of all possible states, right? So just take their weighted sum, weigh them by the probability, and the probability comes from the policy you have defined, which is the epsilon policy. So it should be a one line change. Let's give it a try, uh, and that should give you what is known as expected SARSA. And then we will just instrument that code as well. We will add these few pieces so we get to look at the reward structure. Sorry, the accumulated returns over there. Just takes a five minutes or so, and it should just be a copy paste mostly, with one or two changes. Just copy over the sarsa code and change the update step. Okay, so in terms of changes, this isn't very different from SARSA or Q learning. It's going to look like a blend of the two, right? So the first thing we wanted to change was the update step. That is the sort of whole point of expected SARSA, right? So I still have the commented out code, but this is how it's going to look like now. So all of this is still the same. The only thing that changes is that over here, right? So if you compare this with what we had for SATSA, so over here we were selecting the Q value for some state and action pair, the next state and the next action that we executed or we selected. Over here we don't do that. We just take all the actions in state one. This is the return value for all the actions, and then the probabilities, right? And these probabilities are again being computed in the same way because we still want to use the probabilities from the epsilon VD policy, so they are computed in exactly the same way, right? And we just take the dot product, which gives you a weighted sum of the return values. That is the key change. The other two changes that you would have to make is, of course, now there is no A1 being selected over here, so we can just remove A1 from the updates, and we don't need to generate A1 at all. And A0, of course, becomes this has to happen over here. A0 has to be selected every time, right? The other changes are basically the instrumentation or the extra code we added to print the performance, right? And I ran this for 2000 steps. Again, there were some oscillations. Eventually we did get what looks like something pretty close to an optimal policy. But if you look at the rewards that we have gotten, this one looks sort of better, in the sense that this is very clearly climbing up, and there's a very clear trend that this still has to be trained for more steps. And on the y-axis, if you look at it, this is already able to get you an average reward of -2 or so, right? And what we really want to get is around +5 or something in that vicinity, because the policy is really well trained, then it should be able to get +5 most of the time. Of course, the environment is stochastic, so we won't get a perfect 5, so the average won't quite reach reach +5, but we should be able to get close, and this is very clearly evident over here, right? So this is a small variation gives you another algorithm which might outperform SARSA or Q learning when you are dealing with a stochastic environment like this one, right? This is sort of pretty much everything that we had to cover uh, in this session. So what we essentially know is that what is sort of the key takeaway is that because we have built up an infrastructure and algorithm that is based on sampling and interaction with the environment to learn about the environment, it doesn't really get affected by, at least at this point we believe that it doesn't really have uh, to be changed in any way to deal with environments when there is uncertainty within the environment, right? What we want to do in the next session is take it one step ahead and actually make these make your opponents a little smarter, so they won't be staying in the same place anymore. We will again want that change to be uh, you know a small step or gradual, so we don't want to all of a sudden allow them to move anywhere on the field. That will probably a very big step, and debugging that would be difficult. What we will do instead, we will allow them sort of the freedom to move in one direction. So we can say that okay, probably the defenders can move along their row, or they can move along their column, right? If we want to build a very realistic scenario, then probably I will have some sort of an algorithm, an AI algorithm, or a reinforcement learning algorithm implemented for these agents as well. And it could be this is something that we are going to see much later in one of the other courses, but you could even use the same idea, the same algorithm to train the other agents as well. And that will be very interesting because that gives you six different agents trying to learn something similar, or you can say there's at least uh, they have they have opposing priorities. This agent over here wants to score a goal, these agents want to block the goal, or they want to block the agent. But you can have two different algorithms, two different policies, two different Q tables for these agents over here and for our agent. And that is very interesting. That is that is what they call multi-agent reinforcement learning. We're not going to do that right now, but we will introduce a little bit of freedom over here. We will allow these players to move in their column, and we'll do that in session 2, and then again we will revisit all the computation that we are going to do over here, right? So we'll look at if any of the changes have to be made to our algorithm, our sampling strategy, or anything to account for this fact. But what is really more important is that other than this change, we are going to introduce another change which is going to make it more realistic. And I'm going to talk about that in the next session. But really, just a brief idea is that right now, what we so in the beginning, if you talked about the information that the algorithm needed, to keep track of what just the position of the ball, right? And we hope that by keeping track of this and by interacting with the environment, it would know how the actions affected that state, and how eventually that state would be changed from being over here to being over here, right? That has been the case so far. But when you introduce when you make these agents movable, then now the algorithm has to you can still stick to an algorithm that doesn't care about the movement of the opponents, but that would be just operating like uh, in total darkness. It would be blind to the environment, and we don't really expect the algorithm to be able to learn anything because it's not able to see the rest of the field. So what we want to do is allow it some visibility, and that would mean feeding more information to the algorithm. So rather than just having the position of the ball or the agent, now it should have access to the position of the opponents as well. But then the question really arises is, if we want the algorithm to know everything that is there on the field, do we really want to do that? In this toy game problem, we can do that. We can just have a vector which has the list of vector which has the positions of all the opponents as well. But in to to emulate more realistic scenarios, what we will actually do in the next session is we will restrict how far the agent can sense or how far the agent can see. So we won't pass the algorithm an array with all the positions of all the opponents. We will just let it know if there is an opponent in the four adjoining cells, right? And that is more realistic because in a real world agent, whether it is sensing the game's state, or it is using some sort of visual method. For example, if you're looking at the agent is looking at a gameplay through a camera feed or something. So at any point, it will only be able to observe some part of the field, right? So it's unlikely, it's very unrealistic to assume that it will have access to the entire field, and where are all the players, how are they moving about, and stuff like that. So what we will do is we will restrict it to this the four nearest positions, and that is easier said than done. That actually introduces a lot of complexity uh, to to how we build the algorithm. So far it has been very easy because the state was one of those 20 different integers, but now we will have to think about how to encode this state, because the moment you have different, you can think of this, whatever information there is, you can think of that information as a tuple, right? So perhaps the first value in the tuple is where your agent currently is, the next value is where uh, whether or not the cell north of it is occupied or not, and stuff like that. So if it's a tuple of size 5, then we have to think about how to convert that tuple into an integer, and that is important because we still want to build a table with states and actions in them, and that requires some sort of a hashing or some technique to map from this tuple to a single state, and then a state should really never collide, right? Some sort of an encoding or hashing would be required, uh, and that is where it gets very interesting because right now we are talking about just five different pieces of information: the agent and the four opponents that could be nearby. But what happens if this information is not given to us as integers, right? If we are just looking at a gameplay happening on a screen, on a TV screen, or just taking snapshots of it, then you could still have that partial state observation, but now encoding that, representing that becomes a challenge, right? And that is what we are sort of going to deal with in course 2, which is where you want to learn from pixel based data, right? It could be pixel based, or it could be in any way which is more complex than what you could handle manually. So we will do that in session 2 basically, and that is where it becomes much more interesting, just to see how far your algorithm can go, how what sort of results it can get with an environment where things are moving around, and that will sort of set the foundation for making this even more complex. If we go back and think about the time we said that okay, we will build an environment, we saw that there is indeed such an environment, which is like the Google reinforcement learning environment, the Google football environment, which is a real in the sense that it's much more like a video game, that where you can train your reinforcement learning algorithms, right? So we are sort of going in that direction, because now the next step could be I can make this field even bigger. I can introduce more players, I can introduce more degree of freedom, so the players can just move around in any direction. I can assign, I can introduce more intelligence to these agents, and all of that adds up to the complexity. But we will see that so far, even with the changes that we make in the next session, the algorithm is able to cope up pretty well, right? And the question will be, will it can it still be able to cope up with more changes, if you keep introducing new changes and keep adding complexity? Is the algorithm still able to keep up with them? Which is basically for course 2. We're not going to do that course 1. um, but at this point, given everything we have learned in the last 3 weeks, and the debugging techniques which we mentioned in the last session, and then I just showed you one of the graphs that we can use, and we discussed another one where you can take the delta of the table and plot that to see how much the table is changing and when and how it is saturating. So all of these techniques, these are going to get handy when you start attending the project, right? Uh, the project itself is very simple. It's again a text-based environment, simple. The problem description is very simple, uh, and the problem can be solved without using reinforcement learning. But that is sort of not the point here. Uh, we will attempt it with reinforcement learning. We will use the same algorithms, but the real effort will go into debugging and really understanding the problem. So understand the problem, then tweak your algorithm, and then obviously you will have to debug the algorithm. You will have to select the right parameters to get the right results, and that is sort of the important bit, the takeaway from the course, because you can find the algorithm, you can implement the algorithms, but then getting the desired results, getting satisfactory results, that is what is interesting for us, right? So this like this session sort of over. I will wrap it up, but it's really very important that we get started with the project right now, because it will take time. I can tell you from experience that because of all the work related and other important stuff going on in life, it's difficult to just sit down and implement all of it and debug all of it in one setting. So it will require you a few days, and once everyone turned in their submission, which would be 21st, then after that I'm going to take some time, at least few more days, to just go over the submissions and annotate them with my feedback. But right now we have this window of time. So there is the next session, which we will figure out when to schedule, probably next Tuesday or Thursday. But we don't really have to learn anything new which is relevant to the project. We will learn lot of other things, but it's not relevant to the project. Please get started with your project. If you're facing any difficulties, then please let me know on Slack or email me. Uh, and as you will explore the environment, you'll find out that although on the surface it looks a very simple problem, there are a few things that you will only get to know about when you interact with the environment. Right. With that, I'll stop. I'll take questions if there are any. Otherwise, we can just wrap up a little early.
Karan, tomorrow session is not there, right?
Yeah, because of the holidays.
Okay.
So what I was expecting is because not everyone is here, but I want to run a survey or something and decide if you want to do it on Tuesday, which would just make just everyone will have to take out 2 hours instead of 1 hour for the office hours, or we just want to wait until next Thursday, which will be a really long gap.
Anything is fine, yeah.
I will just post a survey on Slack, and then, based on that, we'll decide.
Thank you, Karan.
Cool. Thank you, everyone. Please do take a look at the project and the rubric and make sure you understand the requirements. Let me know if there's any confusion. And then I'll see you. We'll definitely meet on Tuesday, and then we'll see when the next session has to be done. Cool. Thank you so much. Bye.